welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to be learning about radioactive decay for GCSE Physics. So if you do enjoy the video, feel free to give it a like, share it with someone else, and please do subscribe if you haven't already. Thank you so much for everyone's support. I really do appreciate it. So let's get started. First of all, when we talk about radioactive decay, we have to go back a couple of steps and look at atomic structure, just to refresh our memory. I do have some videos which I'll link at the end for you about this topic in more detail, but just as a bit of an overview, remember the atom itself is not charged, and that's because the number of electrons and protons cancel out. They are in an equal balance. The number of protons, remember each proton has a +1 charge, and it's found in the nucleus of the atom or the center of the atom, along with the neutrons that have no charge. However, neutrons and protons do have relative mass to them compared to, say, the electron, which is much smaller in comparison. And the majority of that mass is located, as I say, in the center of the atom, called the nucleus. Electrons, they have a -1 charge each, and they are found in the electron shells surrounding the nucleus. And they do have the ability to move in those structures, and they also have the ability to be lost and gained from other atoms to allow stability. In today's lesson, however, do remember we are actually talking about atoms which have a nucleus which is actually unstable. So we've talked about stability before in terms of the electron configuration. Maybe one atom needs to gain an electron to become a full outer shell. However, in this case, we're actually talking about the nucleus of the atom being unstable as opposed to the electrons. And I'll talk more about that in today's video as well as we go through. Last but not least, just for this point, if you ever see in the periodic table, you've got two numbers next to each symbol, which represents an element. Remember that the biggest number is the mass number, and this indicates the number of protons and the number of neutrons, whereas the atomic number, the smaller number, is just the number of protons that are there, and therefore also the number of electrons that are there. So in the case of sodium, Na is the symbol for sodium. Sodium is a metal. It has a mass number of 23, so there's 23 in total protons and neutrons collectively if you add them together, and the number of protons in this case is 11. So if you wanted to work out the number of electrons, it would also be 11, as remember the number of protons and the number of electrons is equal. They are balanced in that sense. And also if we want to work out the neutron number, well, all we need to do is do 23, the mass number, minus the atomic number, which is 11. So 23 minus 11, and you'd end up with an answer of 12. And 12 would represent the number of neutrons in this atom of sodium. So let's get into atomic stability and a little bit more detail about radioactive decay. So in the case of stable and unstable nuclei in an atom, we need to think about the balance between the number of protons and the number of neutrons. If there's not enough neutrons to balance out the number of protons, or there's too many as well, this can cause instability within that nucleus, and it can actually cause the atom to emit radiation and start to decay, to kind of become stable. And I'll give some examples of how this happens. Thinking of stable atoms, especially up near the top of the periodic table, a lot of the atoms are a lot smaller. So the number of neutrons and protons are roughly in sync with one another. A really good example of this is actually carbon, because it has an atomic number of 6 and a mass number of 12, which indicates that it has perfect ratios of everything. So 6 protons, 6 neutrons, and 6 electrons as well. But it's really the balance between the neutrons and protons that are the important part here in determining whether this atom actually is stable in terms of the nucleus. Some of the atoms that are lower down in the periodic table, some of those elements, the atoms of those elements are much more unstable because they are larger, and those ratios between the neutrons and the protons have started to shift, and there's differences there. So we're going to talk about how different nuclear radiation occurs and what you need to know for the exam. Okay, so the first type of radiation that you need to know about is actually called alpha decay. And alpha is a particle made up of 2 protons and 2 neutrons. Sometimes we refer to this as a helium nucleus, but be careful you do not say helium atom, because a helium atom would imply that there are electrons involved as well. And we're just talking about those protons and those neutrons. So what actually happens during alpha decay? Well, just remember that we have an unstable nucleus. It could be any type of nucleus, especially those ones that are lower down in the periodic table, those larger atoms. We've got the example here of radium, Ra. It has a mass number of 226 and an atomic number of 88. It will decay by emitting 2 protons and 2 neutrons, or an alpha particle, and it will become a smaller, more stable nucleus in the case of radon, which has an atomic mass of 222 and an atomic number of 86. So just if you just have a quick look at those numbers, you can actually see there's some really important information there that you need to know for your exam. So you can see the difference between radium and radon is the 4 as the mass number and 2 as the atomic number. And that would imply there is alpha decay going on. As you can see, we've got the diagram, the atomic symbol He, which could represent or does represent the alpha particle. You also could have the symbol for alpha as well instead of the helium symbol. It's just worth knowing both in case they give you one or the other. Also, you could be expected to write these out. You could be expected to predict the products that form from alpha decay. There's loads of different examples of things they could ask you to do. So if you would like a follow-up video or maybe a short on this, I'm more than happy to do that. But this is a key example for you. Another thing you do need to know for the exam is kind of the properties of alpha as a particle itself. So you need to know that it's highly ionizing. So it's very dangerous to us. It can actually cause a lot of problems if we're exposed to alpha radiation. It's low penetration in a sense. So although it's highly ionizing, it's low in penetration. So it means it won't be able to travel very far. In fact, it can only really travel less than 5 centimeters in the air, and it's often stopped by things like skin and paper. So it's not hugely problematic, but because of that highly ionizing ability, it can be. Radium and radon, like I said, are the good examples to know for the exam, but there are, of course, lots of others. So like I said, if you would like a follow-up video on some more nuclear radiation equations, I'm more than happy to do that. Just let me know in the comments. So let's talk about the second type of radiation, and this is beta radiation. Beta is actually a fast-moving electron, sometimes called a photon, and it's given the symbol E minus or just the symbol beta from the Greek alphabet. Now, what actually is this? Because essentially, beta is a bit of an unusual one, because what happens in the atomic nucleus of an unstable atom, one of the neutrons will actually split open and it will form an electron or a beta particle and a proton. Now that electron, that beta particle, because it's an electron, students will often think that it's come from the outer shell of the nucleus of that unstable atom, but weirdly enough it doesn't. It comes directly from the nucleus of that atom. It comes from that neutron that has split into the electron and the proton. And this is going into more of the quantum physics realm, but you do need to be aware that that electron has come from the nucleus and not the actual outer shell of electrons. So beta decay often causes a change to the atomic number, but no change to the mass number, because electrons don't have really a large mass comparative to the other subatomic particles. So as you can see, we can say that beta has a 0 atomic mass and a -1 sort of atomic number. And if we put this into our equation, we have some examples here. So here is the example. We've got cesium, which has a mass number of 137 and an atomic number of 55. And this decays by beta decay to form barium, which has a mass number of 137, which is exactly the same as before, but instead now it has an atomic number of 56. And you can see there's been an increase in the atomic number, because actually what's happened is in this case, we've got a -1 from the atomic number of beta decay. So when you add those together, 56 plus or -1, you get that 55. So what we're doing is we're trying to balance out the numbers on the mass and the atomic number, just like you would when you balance equations or you do maths as well. So whatever's on the right-hand side of the arrow must be the same as the left-hand side as well. And that's why beta has a 0 there too. And that's why those 137 mass numbers are unchanged for this equation. The only other thing you need to know about for beta decay are some of the properties, just like we did for alpha. So let's go through those now. So beta decay has low penetration. It's actually stopped by 3 millimeters of aluminium foil, and it is low ionizing as well. It actually is able to travel 1 meter in the air, however, so that is a bit of a comparison point for you when you are doing this in your exam, or you perhaps get asked about some of the properties, and maybe even are asked long answer questions where you compare all 3 of them together. So that's a bit of information for you. So I've saved the best for last. This is the type of radiation that changed Bruce Banner into the Hulk. If there are any Marvel fans out there, hello, welcome, welcome. Whether that actually could happen in real life is debatable and maybe a story for another day. But gamma radiation is a type of radiation that we would define as a high energy particle. It's part of the electromagnetic spectrum. It's actually a wave, which is slightly different from the alpha and beta decay. And this wave of energy is emitted after the nucleus has decayed by alpha or beta decay. Because that nucleus is very hot, that energy needs to be emitted to help it cool down and help become more stable. However, saying that, it doesn't change the mass or atomic number, as you can see in the case of the barium atom, which has a mass number of 137 and an atomic number of 56. Gamma is given the symbol gamma from the Greek alphabet, but there is no change in those numbers there, as you can see. The only other bits of information you need to know for the exam are the different properties of gamma. So you need to know that it has high penetration. It's really only stopped by lead or concrete, which is why a lot of nuclear power stations will be surrounded by those types of materials. We will also learn about the disaster of Chernobyl in a few lessons time, so keep an eye out for that one. I'll link it to this one too. You need to know that it's very low ionizing, as opposed to, say, the other particles which have higher ionizing properties, and it can travel quite far, over a kilometer by the air. So those are some of the other properties that you may be asked about, and you could be asked to compare those properties to the ones of alpha and beta decay as well. Thank you so much for your time today. If you did enjoy the video, please do give it a thumbs up and share it with someone else you know is studying for their GCSE Physics exam very shortly, in the few months that we have left until the exam season really starts to begin. If you are studying your GCSEs, do let me know if you would like any specific videos in the comments section. And if you do want more help, I have some videos I've linked over here, but also my Instagram and TikTok, where I post shorter bite-sized pieces of revision for biology, chemistry and physics GCSE. In the meantime, I've been the GCSE science teacher and you have been curious. I hope you have a fantastic day and I'll catch you in the next one. Thanks so much for your support. Bye.